Okay, so we're actually finally going to get started proving things about computers. But of course, if we want to prove things about computers, the first thing we need to do is define what the heck a computer is. So the plan for this semester is we're going to start with a very, very simple computer and prove things about that computer, and then we'll move on to more complex computers over time. So our first simplest computer is going to be kind of a theoretical computer, and it's going to be a computer that can recognize a language. So let's just remember, right, a language is a set of strings, right? And an alphabet is a finite, very important set of symbols. Okay? And we've also said that lambda is never an element of our alphabet. Okay? Lambda is a special symbol, but it represents the empty string, and we're just going to treat it as a string rather than a symbol. Okay? And so what's our first computer going to do? Well, our first computer is going to take a language and a string, and it's going to say one of two things. It's either going to give us a thumbs up, yep, this string is in this language, or nope, thumbs down, the string is not in this language. So, you may want to ask, could we actually use this computer for anything real? Is there any, okay, it's a theoretical computer. Okay, you're taking a theoretical computer science class. Maybe there's no use for it, but maybe there's something. So before you keep moving on with this video, see if you can think about what you might be able to use a computer that all it could do was tell you if a string was in a language. Well, one thing that it could do is it could recognize an integer, right? So it could tell us whether numbers are integers or not, and we could use that in, say, a Java compiler, right? Or in fact, there's a ton of stuff we could do with a Java compiler, right? Because we could take a look and recognize, we could kind of parse a line of code and decide whether it was syntactically correct, right? We could have a language of syntactically correct lines in Java. And in fact, compilers use sort of simulated computers like this a lot when you're actually designing a compiler. So here's our game plan for today. What we're going to do is I'm going to define this very, very simple kind of language, right? And I'm going to build that theoretical computer that recognizes this language. And we're going to learn to prove things about it. We're going to learn all sorts of different ways to represent computers that recognize this language. And we're going to do that for a while. We're going to do that for like a month and a half even. And once we've done that with the super simple computer that just recognizes this very, very small, specialized set of languages, then we'll move on to the harder languages. Our computer is going to recognize a set of languages called regular languages. So regular languages are about as simple as you can get for our purposes. Now, even though the each individual regular language is fairly simple, there's still an infinite number of them. So this is not completely trivial. So before I explain to you how you can tell whether a language is regular or not, let's just talk about some examples of regular languages. So here's just a few examples I threw together. This first one is a set that just has 4 elements that happen to be the digits 1, 2, 3, and 4, right? So each string in this language is actually just a single letter long, or a single symbol long, I suppose. Another regular language is the set of all words in the English language, which is a very big set, but it's not an infinite set. On the other hand, here's an infinite set. So this is the set of all strings made up just of A's, right? So it's A to the N, such that N is a natural number. So you can have 0 A's because 0 is a natural number, or 1 A, or 2 A's. right? So here's the set that we end up with, right? This is just a nice shorthand to write, way to write this set, right? Lambda's in here because when n is 0, we don't have any a's in at all. When n is 1, we have 1a. When n is 2, we have 2 a's. When n is 3, we have 3 a's, and so on, right? Here's another language that is regular. So what is this language? Just take a look at it for a minute. And it turns out this language is, you have 1a at the beginning, but just 1a, and then you have as many pairs of b's as you like. How many? Well, anything in the natural numbers. So you can have 0 pairs of b's, or 1 pair of b's, or 2 pairs of b's, or, this is 3, right? So an a followed by 6 b's, and so on. Here's another regular language for you. It's just 1, 2, 3, 4. It's a set that has 5 strings in it. Great, that's a regular language. And here's another interesting one. This is a to the n b to the 2m, such that both n and m are natural numbers. So this says start out, let's see, start out by picking n a's, and then pick a number for m, double it, and pick that many b's, and squish them together with the a's before the b's. So here's how I tried to write out that set. When you start writing these sets that are not quite as obvious how to write them as these first two, my approach, you always want to have some sort of a methodical approach if you're going to use these ellipses, these dots, right? My approach is, let's start by writing all the strings of length 0. Is lambda in here? Well, it sure is, because n could be 0 here and m could be 0 here, so that's no a's and no b's. And then are there any strings of length 1? Well, sure, you can have a single a with no b's, so that gives me this guy. Any strings of length 2? Well, I could have 2 a's in a row, or I could have 2 b's in a row, but I can't mix a's and b's yet. What about strings of length 3? Well, I could have 3 a's or an a and 2 b's, and I think that's all I can do, right? Strings of length 4. Well, here it gets a little bit more interesting. I've got 4 a's or 2 a's and 2 b's or 4 b's. But the interesting thing here, when I'm trying to write a set out like this with the dots, with the ellipses, is I want to show you that I understand the set by kind of giving you some sort of pattern. If only that pattern is strings of length 1, strings of length 2, strings of length 3. And then I take a deep breath and say, thank goodness I can also express the set like this, because this is so much easier. So just because a lot of languages are regular doesn't mean all languages are regular. So here's some examples that are kind of weird when you first look at them, right? So I will tell you that the set of all words in the English language, regular. But the set of palindromes over the English language, over the English alphabet, for example, so every single word in the English language, every word in the Oxford English Dictionary, whatever dictionary you pick, regular. But if you take all the letters of the English alphabet and you try and make palindromes out of them, so what do I mean by a palindrome? Words that are the same forwards and backwards. So here's a few examples, right? So A, B, C, C, D, C, C, B, A, same forwards and backwards. D, and then 3 A's, 2 C's, 3 A's, D, same forwards, backwards. C by itself, forwards, backwards, AA, right? If you take the set of every possible one of these, not regular. Okay, what about this language? I say this one is regular, a to the n, b to the 2m, where we've got an n and m here. Here I've got a to the n, b to the 2n with just an n. What's the difference between those two? Because this one's regular, this one is not regular. And if you look at them, of course, the difference is this set on the left, the number of a's are not related to the number of b's in any way, right? I get to pick an n and an m, and as long as both of them are in the natural numbers, then the string that I make with that many a's and that many b's in my language, right? On the right-hand here side, what we have is I only have one number that I'm picking, and they have to match. So I always have twice as many b's as a's in my string. So if we look at the examples of the strings in here, if n is 0 and m is 0, right? Again, I'm trying to show you these in the order, in some order that makes it obvious what happens when you get to the dots, right? Though, of course, this makes it much easier. So strings of length 0 in this, well, if n and m are both 0, then lambda's in there. Strings of length 1, well, it looks like M has to be 0, N is 1, so then we get A, right? Strings of length 2, if I make N2 and M0, I get AA. If I make N0 and M1, right, because it's B to the 2 times 1 is 2, then I get this BB, and so on. So this is a regular language. On the other hand, over here, I just have to choose N. I make N0, I get lambda. I make N1, I get 1A and 2 Bs. I make N2, I get 2 A's and 4 Bs, and so on. Not regular. Kind of weird, but we will talk about that later, why it's not regular. We'll just deal for now. Okay, so let's just talk about these last two. So the set of all integers, big infinite set, regular. The set of all integers in which the number of odd digits is the same as the number of even digits. So, for example, 1, 1, 1, 2, 2, 2. Same. There's three odd digits, 3 even digits, or 1 even digit, 1 odd digit, or 1, 2, 3 even digits and 1, 2, 3 odd digits. Right? This language, not regular. This seems weird, right? So we will talk more about this in a minute, but just know that not all languages are regular. So how are we going to find out whether a language is regular or not? Well, I'm going to give you a list of rules on how to make a regular language. And if you have a language and you want to know, is this regular, you can sort of play with these rules. And if you can put your language together using only my rules, then it's a regular language. If you can't do it, well, maybe it's just you that can't do it, but hopefully if it's impossible to do, then that means it's not regular. If you're just having a bad day and someone else can do it, still regular. So there's a bunch of rules about what makes a language regular. Remember, a language is a set of strings, so we're always going to be talking about sets. Here's the first 3 rules. Rule 1 just says that the empty set is a regular language over an alphabet. So if you have any alphabet, whatever your alphabet is, the empty set, and you ask whether the empty set is a regular language, the answer is yes, because of rule 1 here. For rule 2, we say that this language, the language that just has lambda in it, is a regular language over whatever alphabet you have. Remember that our alphabets never have lambda in them. We specified that. And but lambda by itself, the set containing just lambda, is indeed a regular language. And then the last rule says that for any letter in your alphabet, the set that just contains that letter is a regular language over that alphabet. Okay, so we'll get on to the full definition of regular languages in a minute, but let's start with just these first 3 rules, right? And let's suppose that I have an alphabet that's called F, just so you don't think all alphabets are called A. And F is an alphabet, so it's a set of symbols. So it is, let's see, 1, 2, 3, 4, 5 symbols. The letters R, O, W, A, and N. And my question is, list some regular languages over F. So let's list all the languages that we can get from these 3 rules. The first rule here, pretty simple, right? We end up with the empty set. The second rule, we end up with the set containing lambda. The interesting one is this one, right? So it's the set containing every symbol for any symbol in my alphabet. So in this case, my symbols are R, O, W, A, and N. So the additional sets that I get that might be that are regular over F, given that F is this alphabet, are a set containing R, a set containing O, W, A, and N. And good. So far so good, but I'm sure you're not super excited yet. Just to make a point here, if I asked you what's the set of some regular languages over F, the ones that we know based on rules 1, 2, and 3 now. Now we have a set of sets, right? So I have my set symbols on the outside, and then inside each of the items here is a set, because you remember that that symbol actually represents the empty set. So I can turn it into a set of sets if I want to. Still not, roller coaster thrilling yet, but we're getting there. Okay, so now let's talk about the full list of rules for what makes a regular language. And we're going to use an inductive definition here. And by the way, if I were in the classroom, I would be copying this whole thing onto the board now. You can either open your textbook to page 739 so you have a reference for this for the rest of the lecture. You can take a screenshot of this screen. You can look at the slides that you should be able to download, but somehow it's useful for the rest of today's lecture to have this list of rules for regular languages handy. So it turns out the rules 1, 2, and 3 that I gave you, they're the base cases of an inductive definition, right? An inductive definition just means we're going to build on ourselves. So if you have an alphabet A, first we have all our base cases. Okay, now let's look at the inductive step. And the inductive step says, if you already have 2 regular languages, let's call them L and M, then these 3 other languages that you can build out of L and M are also regular languages. So if you have 2 individual regular languages, L and M, so for example, maybe we have the language A and the language B, and we're talking about, again, our alphabet for this example is going to be the set A, B, C, right? And we happen to have these 2 languages. We'll call that one the language L and that one the language M. This tells us that L union M is also a regular language. So what is L union M? Well, that would be the set containing these 2 strings, A and B. They do happen to be symbols, but in this case we're talking about a language. Language is a set of strings, so these are just strings of length 1. Okay. Another thing that the inductive step tells us is that ML, the 2 sets concatenated together, is a regular language over A. So this tells us that, let me change color. The set B, which is M, concatenated with the set A, and of course we could do it in the other order, but I'm doing M then L because that's what this line happens to say. Of course, we could of course change what we call L and what we call M, but it says this is a regular language. And what is this? Well, this is just the language where you take one thing from here and one thing from here. There is in fact only one thing in each of those, so that's the language containing a single string BA. Okay. And finally, this tells us that L star is a regular language over A. Now this is interesting because this tells us that we can have infinitely, we can have languages that are infinitely long. So for example, if we just change color one more time, we know that this is a regular language, right? And this last rule here tells us that if we have a regular language, we can also star it, right? And in this case, that means that we get lambda, then A, triple A, and so on, right? And so this set here, well, that's a regular language, okay? So this tells us what languages are regular, and it does it using these pretty simple rules. Now, it probably would help you when you're continuing watching this lecture to just kind of have the book open to this page in chapter 11, just so you can see this for a little while. So, just to review, let's suppose my alphabet is just the set containing 2 symbols A and B. If you look at the base case, those 3 rules, what languages do we know that are regular over A? Well, we know there's 4 languages that are regular. There's one, the empty set. Another language is the language just containing lambda. Another language is the language just containing A. And another is the language just containing B. So the base case gives us a set of 4 different languages, right? Each of these is a set of strings. The inductive step gives us a bunch more languages, right? We can now take the union, we can concatenate, we can take the star. So for example, B star, which is, it's a lambda, doesn't look like a great lambda, but lambda, B, 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 and so on, is regular over A. We know we can concatenate, so AB is regular, but that also tells us that the set AB starred is regular, right? What's that? That's the set that starts with lambda, and then we have AB, and then we have AB, AB, and then we have A, B, A, B, A, B, and so on, right? So here I ask you a question. How big is the set of regular languages over A? And keep in mind, each language is a set, right? So here is one language, and that is a set. Here's another language, and oops, and that's a set. Here's another language that's a set, right? And I'm asking you, how many of these are there? How many languages are there that are regular languages over the alphabet A, right? And the answer is there's an infinite number of them, right? Because every time we have something, we can make something bigger using union and concatenation and star. So there's an infinite number of regular languages. Now, you know, considering that I said that we're starting out with a very simple kind of language, these regular languages, it's very simple, but there's still a heck of a lot of them. So here's a question for you. Is this set a regular language? And think about it for a minute. Well, the first thing I've done is this slide is actually a little bit bogus, because I really should say, is it a regular language over the alphabet, and give you an alphabet, maybe over the alphabet A, B, C, right? Because if I don't tell you what my alphabet is, I can't tell you if it's a regular language. And the answer is yes, indeed it is. And here's why. The base case rule gives us that B is a regular language over this alphabet, right? And we can star this regular language, because we know that from the inductive step. And this thing starred is actually what we've got here, right? This is just B star. This is 0 or more times taking something out of here. So there's 0 times taking a string out of here. Here's just going through once and taking a letter. Here's taking 2 letters out of there, and so on. So, yep, this language here is indeed a regular language. This is saying let A be an alphabet, so A is now defined to be ABC, I'm sorry. And I want to prove that A comma BC is a language. Oh, well, is it a language? And I say prove it. Well, sure, it's a language, right? What's a language? A language is a set of strings, right? So I guess, how do I prove that? Let's see. A comma BC is a set of strings. So yeah, I guess it's a language. We're done. This one's a little bit more interesting here. Is it actually a regular language, and can we prove that? And the answer is absolutely, it's a regular language over the alphabet A. And to prove that, what we can do is we can build it up. So we can say, well, A is a regular language. Oops. Over the alphabet A, right? And B is a regular language, and these are all because of the, let's see if I can squish this ever so slightly smaller, hang on. Okay, and why is the set A a regular language over the alphabet A? Well, that's one of the base cases, definitions of regular languages. B is also a regular language over the alphabet A, same reason, base case. Let's give these numbers. That's line 1, that's line 2, that's line 3. C is a regular language over the alphabet A. Again, that's the base case. But that tells us that the set containing BC is these are supposed to be ditto marks, right? Is a regular language over the alphabet A. Why is that? Because we're doing, we took line 2 and line 3, and we used the concatenation rule. right? And so finally, the set containing A and BC is a regular language over the alphabet because we combined line 1 and line 4 and we used the union rule. So there are a couple of different ways we can specify a regular language. It is a language, so it's a set, so we can specify it using set notation like we've always done. But computer scientists always like shorthands, and one thing that I'm going to teach you now is kind of a shortcut. It's called a regular expression. And regular expressions are a way to represent regular languages. Really, we use them because they're just a little bit easier to write. We don't have quite so many curly braces and stuff. In fact, we don't have any curly braces, but we save a little bit of writing time. So somebody came up with this idea of a regular expression. If you've taken lab techniques or some other courses, you may have heard of regular expressions before. What I'm going to teach you is similar but not identical. Before we talk about regular expressions, I'm going to let you in on a big secret, okay? If you have a regular language, there is a way to represent it with a regular expression. Furthermore, if you have a regular expression, that represents some regular language. So you can go back and forth. If you have a regular language, you can turn it into a regular expression. And if you have a regular expression, you can turn it into a regular language. It actually represents a regular language. So I think it's way easier to understand regular expressions if we just start by looking at some examples of them, and then we can talk about how you formally, if you have a regular language, how you make sure that you find the equivalent regular expression for that. And really, the regular expressions are trying to make our lives easier. So if you have the language that is the set containing a single symbol like A, the regular expression for that is just the A without the set curly braces. And if you have more than one thing in that set, like you have A comma B, you could just say A plus B. So this isn't math plus, this is regular expression plus. And if we have A, B, C, we can write A plus B plus C, right? Now, just like in math, we start to have some problems with rules of precedence. Is this A plus B plus C? Do we do this one first? Do we do this one first? And the good news is we're going to use similar rules of precedence that we use in math to use for our regular expressions. And so we're going to associate these things from left to right, just like with math. So A plus B plus C is really add the first two and then add the last one. When I use the word add, I don't really mean do the math add, because remember, what am I trying to do? I'm trying to come up with a shorthand for a language. So if my set is A comma B comma C, then here's a regular expression that represents that set. And this regular expression actually is shorthand for this one, right? Here's something else interesting. Union is really kind of plus in regular expression world. So the set containing A is just an A. The set containing B and C is B plus C. And I can use parentheses wherever I want to show which go together. So A union B comma C is the same as A plus B plus C. But of course, well, I guess not of course, but guess what? In regular expression land, this plus symbol is associative. So A plus B plus C is the same as A plus B and then plus C, but it actually turns out to be equal to A plus then B plus C. So what about this thing? It's the set A comma B concatenated with the set B comma C. I can show you what the equivalent regular expression is. We just write the regular expression that represents the set A comma B, so that's just A plus B. And we dot that with, so this is a dot with the regular expression that represents this set, the set BC. And the cool thing is that you can think of this dot when you're trying to think about precedence rules. similar to times in math, just like we'll kind of think of this similar to plus. They don't really mean mathematical times and mathematical plus by any means, but it can be useful when you're trying to figure out rules of precedence to just think of them that way. And in fact, pretty quickly, we're going to get lazy and we're not going to write most dots. Just like in math, you don't write a dot when you have like 3x. You never write 3 times x. You just write 3x, right? So we're going to get lazy very quickly and not write this dot. But, and then it'll just look like this, right? But you have to remember there's a dot in there, and that dot is a concatenation dot. But we're going to leave it in there for now just so you remember it's there, because you're just starting out. I want you to remember the dot. Now, the big question that I have for you is, do you actually know what single set this represents? What are the things that are in this set, right? This is this set concatenated with that set, right? And that turns out to take one thing from here and one thing from here, right? So we have A followed by B, or A followed by C, or B followed by B, or B followed by C, right? And of course, since this set is the same as this set, it's just written in a slightly different way. We have another different way to write this A plus B starred with B plus C, which is just, we can write AB plus AC plus BB plus BC, because this regular expression represents this set here. Here's an easy one. If I have a string Rowan and another string rules in my set, so just a set containing 2 strings, I can just say Rowan plus rules. It's just the 2 strings added together, right? And you can see here, add plus really kind of means union, right? So it's the set containing Rowan unioned with the set containing rules is one way to think about it. Now, strictly speaking, the way you should write this is actually using the dot operator, which is concatenation, or as I like to call it, the squish operator, to say, all right, well, we're going to take each of these letters and squish them together, and we'll union that with each of these letters squished together. And just to be so insanely OCD, I'm going to put those parentheses on. But, you know, you think about it a little more, and because of the rules of precedence that I told you, that this dot operator actually has a higher precedence than the plus operator, just kind of like times has a higher precedence over math plus. We don't really need those braces in there. And the truth is, we're going to get rid of all these dots. If we have a string, we're just writing it as a string, because to my mind, the real reason we use these regular expressions is to make our lives easier, and that sure as heck is not making things easier. Okay, here's something a little bit different. I've got the set AB starred. Let's remember that the set AB quantity starred is really equivalent to 0 or more copies of the stuff in that set, right? So I've got lambda or AB or ABAB or ABABABAB, right? On and on. And as a regular expression, it's easy. We just write AB star, right? AB quantity starred. And there is no idea of ... over in regular expression world, so we can't do this one. We just need to write AB starred. The other thing that there isn't over in regular expression world is the plus that we can do on sets. Remember, we had the plus, which meant 1 or more, right? Not 0, not including lambda. We can't do plus over here. The only operators we have to work with are star, dot, and plus. Now, one last thing on this slide, AB star, it's really important that you recognize that AB star is different from this guy, right? So AB quantity starred versus AB star. This one, the star, think of it like an exponent. It binds very tightly to whatever it's next to. So when we have AB star here, that is the same as the set containing A followed by the set containing B quantity starred. In other words, it's this language, right? 1A or an A and 1B, right? So it's an A and 0 B's, an A and 1B, an A and 2 B's, and so on. So very important. Whether you're working with sets or with regular expressions, you're going to have to be able to tell the difference between these things. Now, right now, I'm just showing you some examples. We're going to do a lot more examples of how to switch between a language and the equivalent regular expression. So don't feel like you have to know exactly how to do this yet, but I just wanted to give you a feel for what's going on before we get a little bit more detailed. So we're going to use this L of notation to mean the language of. So L of Q is the language of the regular expression Q. In other words, if I have a regular expression Q, what is the set that corresponds to Q? So I might say the language of A plus B plus C, right? Where A plus B plus C, this is a regular expression. Its language is this set. This is a regular expression. Its language, the language of this is this set. Here's another regular expression. Here is the set that it represents. This is actually the concatenation of two sets, but that represents a single set, right? It represents a language. Here's the regular expression for this language. The language of this regular expression equals that. Now, let's just be very clear here. This equation is not true. The Rowan plus rocks does not equal the set Rowan comma rocks, right? The regular expression Rowan plus rocks does not equal the set Rowan comma rocks. However, the language of this regular expression equals that set. So a set and a regular expression are two different things. It just so happens that we have a way to convert between them. The language of a regular expression equals a set. So you might actually, just from these few examples, be able to figure out what most regular expressions are. But there's one set that I haven't told you about yet, and that's the empty set. If you have the empty set, then, and I ask you what's the language, what's the regular expression that represents the empty set so that I could say the language of that weird regular expression equals this thing. You don't know yet and you can't figure it out. What I will tell you is we're going to use the same symbol to represent a regular expression of a language that doesn't have anything in it and the set itself. And this is hideous. It was a bad choice. You get used to it eventually, but, yeah, when we're talking about sets, we can talk about this symbol or two sets. And when we're talking about regular expressions, we can only talk about this symbol. Let me explain why I threw these two guys up here. If you see this symbol here, these two set signs here, floating in space somewhere, you know for sure that's a set. Because in regular expression land, we never have curly braces. On the other hand, if you see this thing that you would normally call the empty set, but you're in my class, you're working with languages, so it might be a set or it might be a regular expression. We don't know. Is this the regular expression that represents this set here, right? Or is it this set here itself, right? So we're using, we've been doing this all the time, right? Using the same symbols to mean different things. Just doing it again, I'm sorry. So let's go into the formal definition of a regular expression now. So when you look at this formal definition, you're going to see the formal definition of a regular expression looks very much like the formal definition of a regular language. And of course, that's because they're very similar, right? They're related. As I said before, every regular expression has a corresponding language that's a regular language. Every regular language can be represented with a regular expression. And again, if I were in the classroom, I would be copying this on the board. You can look on page 740 of the textbook and compare this with the inductive definition of a regular language, right? But right now, if you look at this, I'm not telling you that regular expressions have anything to do with regular languages. That's the weird part about this thing in the book. As far as you know, regular expression is just something totally different, and now I'm going to tell you about that, okay? So here are all the different kinds of regular expressions you can have. You can have this empty set symbol by itself. That represents a regular expression. You and I know it actually represents the empty set, the language, but right now this is just one option for a regular expression. Lambda is just another option for a regular expression. And if you have an alphabet A, then and little a is in big A, it's an element of your alphabet, then little a by itself is a regular expression over that alphabet, right? And then we have our inductive step, just the same way we did with our regular languages. If you have two regular expressions, well, you could take one of them and put parentheses around it. You saw me doing that earlier. You can put a plus sign between the two regular expressions. You can put this dot operator between the two regular expressions, and you can star the regular expression. You can star one of them, right? You could, of course, put an S here and say, ooh, S star is also a regular expression over A. But star is a unary operator. It just takes one thing, right? As opposed to dot, which takes two. It's a binary operator. Now, I told you this before, but I just want to remind you, we have this funky dot that we use that I told you is part of a regular expression. And we're going to stop writing it. Just like if you think of the dot as times in math, people stop writing it very quickly. If they say A times B, they don't write A dot B. They just write AB. And when they're talking about A dot B dot C plus C dot B, they just write ABC plus CB. And we're going to do exactly the same thing here. We're going to leave out the dots. I usually put in parentheses if I'm doing anything complicated, but you can get rid of the parentheses. So here's kind of the reverse question. I said add parentheses and dots to the following regular expression to show order of evaluation. So let me just write it out a little bit bigger. So we've got A plus, and I know that there's going to be dots in there, B dot A star, right? And if we look at this, star has the tightest binding. So this A is going to get starred. That A star is going to happen before anything else. And then dot happens, so then we would do that. And finally, we would evaluate the plus. Okay, so I've shown you a ton of examples about here's some regular expressions, here's the regular languages they represent and whatnot, but now let's get formal. We had a formal definition of what a regular expression is. Let's talk about their relationship to regular languages more formally. Remember, when we have a regular expression E, we associate that with a regular language, and we call that the language of E. So we use this L of E notation. Like we said, the language of A plus B, the regular expression A plus B, is equal to this set. Here is an actual language. Here's a regular expression that's equivalent to it. The language of this regular expression is this set. So formally, here's the procedure. If you have a regular expression, and if your regular expression happens to be the empty set, then, well, the language of that regular expression is just the empty set. If your regular expression is lambda, then the language of this regular expression, that's the set containing lambda. Okay? If you have a particular symbol A that's in your alphabet, the language of that symbol, you got it, right? The set containing that symbol. If you happen to have two regular expressions that you add together, what's the language of those two regular expressions added together? Well, it's the union of whatever language you get by just looking at the individual pieces, right? And this is where I said plus corresponds to union. Similarly, I said dot corresponds to concatenation. If you have two regular expressions that are dotted, you can translate the language of the dot of those two just by taking the language of the first one and concatenating it with the language of the second, right? And similarly, the star, the language of something starred, is just whatever you get, taking the language on its own and starring it. So here's three problems. It says find a language, that is a set of strings, to describe each of the following regular expressions. So let's see. So the first regular expression that we have is this A plus BC. Keeping in mind that plus is union, this corresponds to the set A unioned with the set containing a single string BC. Or another way to write this is just A comma BC. Let's change color. This next one here, AB star plus C. Remember, star binds more tightly than dot or plus. This is saying take the language A, concatenate it with the language B starred, right, and union that with the set containing just C. So what does that mean? That means there's two types of strings in this language. The first is just the string C. And the second is an A followed by 0 or more B's. And let's do this last one here. This says 0 or more A's followed by the set containing B followed by 0 or more C's, so that's A starred concatenated with the set that just has a B in it, concatenated with C star. You can see why we developed these regular expressions, because writing this out is pretty nasty. And we're going to take that whole thing and we're going to union it with the set that just has one string, AC. Now, if you want, we can write the second two sets just a little bit more cleanly. Or maybe I shouldn't say cleanly. This is quite clean, actually, but in a way that may make it easier for you to understand. This first set is, let's see, you have an A, and then an A with one B, and then an A with two B's, and then an A with three B's, and so on, unioned with language C. And this next one, the purple one, it gets pretty rough pretty quickly. And what I want you to do is I want you to have a logical order that you specify these strings in. Okay? So the logical order that I find the easiest to use is length of string. So I say, so we're gonna do something union the string AC. But to represent this piece, look at it and say, are there any strings of length 0 in this concatenation? And the answer is no, because we always have a B. So I'll start with just a B. And then I'm going to list all the strings that are of length 2. So I guess there's an A followed by a B, where we take 0 C's, or 0 A's, but we have a BC. And then let's talk about all the strings that are of length 3. So let's see, we could have an A and a B and a C, or we could have two A's and a B, or a B and two C's, and I guess I better ... it at this point, union with that AC. Let's do an example the other way now. We've got a language and we want to have a regular expression that describes it. So this first problem here, part B, has just 3 strings, right? We have the string AA, the string AB, and the string AC. And so this is a language that just has 3 strings. It's made up of just 3 strings. And there's a couple of different ways we can represent that. We could just have the 3 strings plussed together for a regular expression. Or in fact, we could represent it like this, where we sort of simplify it a little bit. So now take a look at this one. What do you see? We've got a single A, and then we have 3, and then we have 5, and it says A to the 2n plus 1. And I guess really this should say, you know, somewhere in here, it should say such that n is an element of the natural numbers. So we've got 1A, we've got 3, we've got 5. Think about how do you represent that? And here's your answer. It's a nice little regular expression, right? Basically, what I'm saying here is you definitely have one A, and then you have 0 or more copies of two A's in a row. So if you have an A with 0 copies of this, that's just this A. If you have an A with 1 copy, that's this guy. An A with 2 double A's, this one, and so on. So here's an interesting language. Let's see what have we got here. We've got lambda, and then it looks like all strings of length 1 made up just of A, B, or C, all strings of length 2 made up of just A's, B's, and C's, all strings of length n made up of just A's, B's, and C's, and I suppose really, again, I should say such that n is an element of the natural numbers. So can you think of what's the regular expression that corresponds to this particular language? I'll give you a hint, and I'll say that this language that we have here is exactly the same as this one, unioned with this one, unioned with this one. And before, oops, that should be 2 C's, 3 C's, and so on. Before you keep going, pause the video, convince yourself that I'm right here. And hopefully you convinced yourself that I was right, and maybe you even saw that that was just, you know, this A star corresponds to the set A starred, union with the set B starred, union with the set C starred. So now it's getting even more interesting. What have we got here? We've got find a regular expression that describes the language. So what do we got here? We have a to the 2k. So what is that? Let's just make sure we know. So that would be, I guess if k is 0, that would be lambda. And if k is 1, that would be AA. And if k is 2, that would be 4. And we're unioning that with this piece, which is b to the 2k plus 1. So we're unioning it with odd numbers of b's. So 1b, 3 b's, no lambda here, right? 5, 3, 4, 5, and some dot, dot, dots. And a closed curly brace. So how do we turn that into a regular expression, right? And in fact, before I make that change, let me ask you a question. I used k in both of these equations, and my question is, could I use different letters? Could I use say a q over here and an r over here? So you may want to pause and think about it for a minute before I give you the answer. The answer is absolutely, because these are two distinct sets. So in this set, it says, it's kind of like local variables in Java, right? This k is only in scope over this set. And this k here is only in scope in this set. So if we changed, say, this k to an r and that one to an r, then it would mean exactly the same. There's nothing here that says that there's some relationship between the number of A's and the number of B's. This is all of those strings that have an even number of A's, and this is all of those strings that have an odd number of B's. So here you go. Strings with an even number of A's, well, it is 0 or more copies of two A's together. Strings with an odd number of B's, well, you start with one B no matter what, and then you add as many more pairs from 0 up to as big as you like of double B's, and you end up with an odd number of B's. And of course we've got the plus sign in here because we're taking the union. Now here's a fun one. This says we want to find a regular expression for the language over the alphabet AB, and it's a language of all strings whose length is a multiple of 3. So here's one way to do it. What I did is I listed all the strings of length 3 that exist over the alphabet AB. And then I said, now take 0 or more of these. And I said that by taking a star. And notice that every time we go in here, we can take a different number of them. So let me just clean this. So, for example, the string AAA, ABBBAA, this long string, is in this language. Because what I did is the first time I took a string out of here, I took AAA. Second time I came in, I picked a different one. I picked ABB. And the next time I came in, I picked BBA. Right? And so you can pick as many, you can go in here as many times as you want and pick as many strings. That's the magic of the star. And you can pick a different string each time. Now, let me clean this up just one more time, because now I'll show you something kind of sneaky. This is certainly, this regular expression we have here is definitely all strings whose length is a multiple of 3. But so is this one, and this is kind of sweet. This says you have to pick an A or B and concatenate that with picking another A or B and concatenate that with picking another A or B. So this little inner piece gives us 3 letters in a row, and it can be any 3 letters in any order over the alphabet AB. And then we have this star out here which says now take 0 more copies of it. So this regular expression up here, perfectly acceptable. This regular expression down here, that I'll clean up so you can look at it again. It's just a very sweet, neat way to write it. Okay, last one. This one is pretty tricky. It says strings with an odd number of A's. And this is really hard to come up with on your own. If you try, you should pause and try and see if you can do this, but don't be discouraged if you can't at first. This is one of those things where you see it done, you see a couple of examples, and then this kind of thing gets a little bit easier to do. Let me expand it a bit so that you can really see what's going on here. Strings with an odd number of A's. So what is this expression telling me? It's saying start out with 0 or more B's, as many B's as you want, right? Because we don't care about the number of B's. Have to have some A's, but we're going to start out with B's. After that, put an A. And after that, as many more B's as you want. So right now, just this first piece, if I look at that first piece, what I've got here, let me get rid of that little circling a little bit again. If I just look at this first piece here, I've got all strings that have 1 A in them, right? And they could have 0 or more B's, and the B's can be in front and the B's can be behind. Right? So I start out with a single A. And then the second piece, this is very clever, because I say, now take as many more of these things as you like, because I've got this star here around the whole parenthesized piece. And this thing says, start with a B, then have an A, right? Start with 0 or more B's, then stuff an A in. Start with have another 0 or more B's, then stuff an A in. Then another 0 or more B's in here. So the whole idea here is we definitely have 2 A's. If you're going to put in 1 A, you got to put in 2. And you can put in as many B's all over the place as you want. So let me just clean that up for you. And you can take a look at it again. Strings with an odd number of A's. So it's strings that have at least 1 A. You have to have 1 A there. And then 0 or more extra bits in there with at least 2 A's each time so that we stay odd.